previous video, we analyzed the concentrated pile placements and crane movement paths using a 3D modeling model. We also investigated how the cranes safely lifted the modules and covered the installation of the elevator core and pedestrian street core, which form the backbone of Habitat 67. Additionally, we delved into the clusters previously mentioned and gained more insight into the considerations taken during the stacking of the modules. In this video, we will explore how the modules, elevator cores, and pedestrian street cores used in the construction of Habitat 67 are interconnected and bonded to each other. Specifically, we will focus on the application of post-tensioning techniques within the modules and the connections between modules. First, we will briefly introduce the most important and fundamental post-tensioning method regarding the connection and bonding of Habitat 67. Before pouring concrete, a duct for accommodating pre-stressed steel strands is placed. Then, concrete is poured and cured, and PS strands are inserted into the duct. The inserted strands are tensioned to provide pre-stress to the concrete. Tensioning of the PS strands is done using tensioning equipment such as pumps. Once tensioned, anchorages such as screws or wedges need to be installed. The post-tensioning method requires anchorages to secure the steel to the concrete, but since the PS strands are tensioned after the concrete has set, it is suitable for on-site construction. This method allows flexibility in choosing the number and layout of PS strands and enables the construction of various shapes of members. This diagram shows how the post-tensioned cables run through the concrete of each unit. It also shows where the steel rows would be placed in order to stack the units. First, we will divide the diagram into sections A to D and explain how the post-tension cables are connected within the concrete of a single module in each section. Then, we will describe how these modules are tied to other modules through steel rows. Let's begin by looking at Section A. Upon closer examination of Section A, we can see that it closely resembles the current modeling. Using the bar grid, bars are securely fixed within the member at predetermined locations. The bars fixed in Section A are connected all the way to Section B. Let's take a closer look at Section B. Section B is where the post-tensioning method described earlier is employed. Similar to Section A, bar grids are used to secure bars at predetermined locations, and Section B is positioned on the walls of the two modules to be connected. Within the T-shaped section of Section B, holes are also drilled for two reinforcing bars. After fixing the bars in Section A, the opposite side in Section B is pulled by a post-tensioning machine, and then the protruding parts of the bars are cut, filled with grout, and finally finished with sealant. So far, we've examined where the post-tension cables were installed inside the modules and how they were installed, as well as how the final finishing was done after installation. Now, let's explore how these modules are connected and bonded to each other when stacked vertically, horizontally, or side by side. The joints where modules are connected are indicated by sections C and D in the current modeling. Let's first examine section D. Firstly, as seen in the modeling, the current area indicated by the arrow represents the outer face of the lower module. The portion currently marked in red denotes a pipe sleeve with a diameter of approximately 90 mm, within which fits a pin measuring about 65 mm in diameter and approximately 400 mm in length. The section highlighted in red represents a steel plate positioned at the joint between modules, with sponge rubber and neoprene pads placed adjacent to it and above it respectively. All the structures described are secured by several reinforcing bars with a diameter of approximately 13 mm. Finally, high-strength grout is injected between the pipe sleeve and the pin via an approximately 13 mm diameter grouting tube located at the top, firmly and robustly bonding the two modules together. When stacking modules on top of each other, steel plates, sponge rubber, neoprene pads, and similar materials are used between the modules. The reasons for using these materials are as follows. First, they reduce vibrations between modules, increasing stability. Second, they decrease friction between modules caused by various impacts or external factors, thereby enhancing the building's durability. Additionally, these materials compensate for any imbalance that may occur during the stacking process, ensuring safe stacking. Therefore, the use of steel plates, sponge rubber, neoprene pads, and similar materials contributes to enhancing the structural stability and durability of Habitat 67. So far, we've covered the explanation of Section D. Now, finally, let's delve into Section C while revisiting the details mentioned in Section D. We will also explore how the connections between modules were achieved overall. In Section C, we focused only on the areas where modules are in direct contact with each other. Now, in Section D, we will explore not only the points of contact between modules, but also how the connection between modules is achieved overall. First, in the plan view of Section C, you can see that there are two reinforcing bars embedded in the rectangular frame at the center of the wall, with grouting tubes on either side of the rectangular frame. The modeling you are currently viewing is a vertical section of Section C. First, the lower section is the lower module, and the upper section is the upper module. The part indicated by the arrow is the grouting tube you saw in the plan view of Section C earlier. The part represented by the red line is approximately a 25 mm diameter tendon, and the two tendons are fixed to the upper steel plate. Similarly, the void space between the concrete and the tendon is filled and firmly secured using high-strength grout injected through the grouting tube. Now, let's take a closer look at the parts where the modules are directly connected. The part indicated by the arrow is the coupler shield. The coupler shield is one of the accessories used for rebar connections, typically used when connecting two rebars to create a longer one. The coupler shield is used to protect the connected rebars and ensure a safe connection. Above the coupler shield is the end shield, which is also an accessory used for rebar connections. Typically, it is used to protect the end of the rebar and ensure a safe connection. The end shield covers the exposed end of the rebar, increasing its safety and preventing damage during the rebar connection process. In the section where the modules directly meet, you can see that steel plates, sponge rubber, and neoprene pads introduced in Section D are used. The currently displayed part is asphalt coated. The asphalt coating around the junctions of modules in Habitat 67 serves two main purposes: waterproofing and surface protection. It helps prevent water infiltration and dust accumulation, enhancing durability and protecting the structure from environmental elements. Additionally, it safeguards the integrity of the junctions, extending the lifespan of the building. Finally, at the bottom, you can see the anchor plate sized 100 mm by 100 mm by 6 mm, which securely ties together the structures mentioned above. We've now completed the explanation up to Section C. From Section A to Section D, we've explored the post-tension connections within the modules used in the construction of Habitat 67, as well as how these modules are connected and bonded when stacked together. In summary, we discovered that the modules of Habitat 67 are securely bound internally through the post-tensioning method, and we explored how the connections and bonding between modules were established. Additionally, we confirmed the use of high-strength grout and sealant in the finishing work, along with asphalt coating around the junction areas. Almost every part of Habitat 67 is constructed using modules. Naturally, not only the modules introduced today, but also the elevator core, pedestrian street, and even the stairs are all constructed using modules. In next week's video, we will take a closer look at the connections and bonding between the modules and the elevator core, between the modules and the pedestrian street, and between the elevator core and the pedestrian street in this modular construction. Thank you very much for listening to our Team 7 presentation.